Okay, so when we're reviewing the myosin, when you look at the myosin pieces, on the ends of the myosin there are two binding sites. What were they? They bind to actin, and it's an enzyme that breaks apart something for energy, an ATPase. So it binds to actin and ATP. When we talked about the binding sites on actin, they're a little bit different. The actin itself, remember, is like a chain of pearls, which is thinner, more delicate, more fragile, and it had a binding site on it that one part of it wants to bind to, if it's actin, it wants to bind to what? Myosin. And then that other thing started with a T. Do you remember what it was? Troponin. Yep. So it's bound to troponin. And then here's that little troponin molecule. And troponin, remember, was like the hinge that allowed what to move out of the plate, out of the way? It allows tropomyosin to move out of the way. And then today we're talking about that whole process of how troponin, tropomyosin, actin, and myosin all work together. And I played this for you last week. You can see that there's the myosin head, there's the calcium that comes in. What's calcium have to bind to? What receptor for calcium, right? On what? What's this thing? It's troponin. When it binds to troponin, it allows troponin to act like that hinge and move the tropomyosin out of the way. So then you see these little myosin binding sites. The myosin head grabs a hold of the myosin binding site and actually pulls. Like a hand on a rope. It grabs a hold of the rope and gives it a little bit of a pull. You don't have just one myosin head grabbing and pulling, because otherwise that would be pretty limited. You go like this and that'd be it. So you have one that pulls back and you have another one that will reach forward and grab and just keep doing hand over hand over hand. And I'm using two hands as an example, but literally on that myosin I just showed you a few slides back, there are actually thousands or hundreds of thousands of those hands that keep going hand over hand over hand, trying to pull the actin in. It's acting like a super tug of war. Huh?
And does that band twist?
The myosin band doesn't twist.
It doesn't
Nope. Nope twisting, no bending, no warping, no scrunching, no nothing. Remember when I gave you the example before, it was like my fingers. If I take my palms and I say the palms are the Z line, and this is the actin and the myosin, as I pull these together, did either of them shorten? Did my fingers shorten at all?
No.
No, it'd be painful if I shortened my fingers and broke my fingers, right? And I don't bend my fingers either, do I? My fingers stay straight, but what happened to these Z lines? They get closer together. So the sarcomere overall shortens because the actin and the myosin do what? Do they bend? Nope. Do they warp? Do they stretch? What are they doing? They're sliding over each other, right? So they're sliding over it. And we'll talk about that process today too. It's called the sliding filament theory. Okay, so we just played this clip. And the question. I think we ended on this last time, but this is a refresher. The cross bridge of the myosin binds to what two things? It binds to ATP and actin. Right? Okay. How about this? Which is not true of a cross bridge? How about this? Cross bridges bind to actin during muscle contraction. They do that, right? They bind. How about this one? Cross bridges are formed by the globular heads of the myosin. That's also true. We call them the head or the cross bridge. How about cross bridges consist of troponin and tropomyosin? Cross bridge, troponin, and tropomyosin. No. Troponin and tropomyosin are over on the actin, remember? Yeah. This is the only thing that does any changing. That little bend is just the hand. Did the myosin itself bind? Bend? Does myosin bend?
No.
No. But when you're bending your hand to pull a rope, you bend that little tiny bit, and that's it. It's the only part that you actually do any bending. So if we went through and crossed these out, cross bridges bind to actin during muscle contraction. We absolutely know it does. Cross bridges are formed by globular heads. Absolutely is. And this is the big no. This does bend just a little bit. This one definitely is on actin, so you know it's not troponin, tropomyosin. All right. The bridge itself will do a little bending, but the myosin itself does not the myosin. And the next is that sliding filament theory that we were just mentioning. When you look at the filaments, this is not moving on my picture, but there we go. So up here, look at the actin itself. Does the actin change its length?
No.
Nope. What do you call this long bar through here? That's the myosin with the little tiny, what are those things called? Those little, I can't tell you either their names. without giving it away. This is myosin, right? So you have these little tiny golf club structure thingies on the ends. They're the cross bridges, the heads, right? So when you look at this, the overall length of the myosin, did it change? Nope. The overall length of actin, did it change?
No.
Nope. Did the overall length of the sarcomere change?
No.
Yes. Yep. So the sarcomere itself actually shortens or lengthens, but it's not because of the actin and the myosin changing lengths, because they're doing what? Sliding over each other, which is why they call it the sliding filament theory. Right. Did the Z line itself bend or warp? Nope. Did the I band change its length? So the I band's from here over to here. Yes, it does. Does the A band change its length? So from this end of the myosin to the other end of the myosin, does it change length? Nope. What's the name of the piece that's missing that goes right down the middle of the myosin? The M line. Yeah. There's a reason I keep going over these parts with you again and again and again. I'll let you figure out what it is. All right, but when you look, the A band itself doesn't change. The actin filament doesn't change. The sarcomere shortens. Right. The H zone, where's the H zone at? The H zone is the space in between the actins. So there's an actin here, there's an actin here. That H zone, is it changing?
Yes.
Yes. So as the sarcomere shortens, the H zone shortens, and what other area shortens? The I band. So as the sarcomere shortens, the H zone shortens, and so does the I band.
Well, the only ones that don't change are A band and M line.
Actually, I would just think the only things that do change, the H zone, the I band, and the length of the sarcomere. Everything else stays fixed. The M line doesn't change, the actin doesn't change, the myosin doesn't change, the A band doesn't change, the Z lines don't change. So the overall contraction is because the thin filaments are sliding closer together. They're pulling over the myosin, moving across in that sliding filament action. So your book shows a picture like this. I like the moving picture better, but here you can see, what's this band called from here to here? A band. Did it shorten at all? Nope. What do you call that little zone in between this actin and this actin? That's the H zone. Does it change when the sarcomere shortens? Yes, it does. Okay, the Z line you can see stays pretty fixed. Okay, it doesn't move, it doesn't wobble. How about the M line? Does it move? Nope. It's right in the middle of what? The A band or the myosin filaments, right? So if I were to ask you a question like that, when a muscle contracts, which of the following happens? How about number one, true or false? So what do you do with it? Get rid of it. All right, next, the myosin filament shortens and coils up. Nope. Cross that one out. How about myosin slides over actin, making the A band smaller? What was wrong with that? The A band does not get smaller. See number one. So we know number 1, 2, and 3 are wrong, but double check number 4. Does the H zone get smaller?
Yes.
What's the other area that gets smaller?
I band.
The I band. The overall, it shortens the sarcomere, right? So if we take just one of those cross-bridge heads and look at it, there's moving through. Here's your actin, your chain of pearls. Here's one cross-bridge head. Do you have just one cross-bridge head on a myosin? Nope, you have thousands or hundreds of thousands. You have tons and tons of these things. You can see all the pieces flying in place. What's this blue strip? That's the tropomyosin. So what must this like maroon-colored hinge be? It's the troponin. So what would this thing coming in and stimulating myosin be? It's ATP. Look at that. Why is it splitting? A third of it's flying off. Because when you break apart ATP, what's it turn into? ADP. Right, so you take the ATP and you remove one of the phosphates. Watch it. Zoom. You steal its energy and you throw off that extra phosphate. And then you have to break off this ADP, which is adenosine diphosphate, and go back and recycle it somewhere else. This little cylinder that's flying in here, this process of breaking things apart almost everywhere in the body revolves around water molecules. So water's flying in and helping break that ATP apart. And the water flies off. So what's this yellow ball then? Yep, the yellow ball that flies in, hits that hinge and causes the hinge to pivot is called calcium. So your book, since it doesn't actually move, shows it one step at a time. Here you can see the myosin stays its length, but the cross bridge itself pivots just slightly. So what it'll do is it'll grab a hold of one of those little pearls, grabs a hold of it, and bends back one click. When it's ready to go on to the next one, it lets go, moves to the next one, grabs that, and comes back one click. So it detaches, it moves back into its, what they call the cocked position, and then they pull one more. And it keeps doing that one at a time. It's like the myosin's my arm. I'm not moving my arm, but I'm just moving my hand and going pull, pull, pull. But I have two arms, right? So I can go pull, pull. As one's grabbing and pulling, what do you think the other one's doing? Releasing and reaching. Exactly. Then when it grabs a hold, this one lets go, and they keep switching that position. Just hand over hand, basically. Like a tug of war. I can't think of any better example. And you can just see the myosin itself is fixed, but those little cross bridges wobble a little bit. So they keep going hand over hand, pulling the actin into the middle. And of course, do you have just one myosin per muscle fiber? Nope, you have thousands and thousands of them. So here's a myosin down the center, and remember the myosin in the cylinder, it's surrounded by actins. So you actually have these little cross bridges surrounding the myosin, and they're constantly pulling on tons of little ropes around all at the same time. So it's a really efficient process. It's not just hand, hand, hand. It's lightning fast. Like a millipede using all of its feet at one time and moving. Okay. Look, steps. What do you know? Put a star by it. Right. You need to know steps. Okay, so the steps, and I've already walked through the steps with you, but here they are organized. So the first thing is ATP is hydrolyzed. What's hydro referring to? That water molecule, right? Lyse means to break apart. So ATP, adenosine triphosphate, gets one phosphate stolen off, and the energy that was holding the phosphate together is released to charge this little myosin head. It's like an electromagnet. When you zap it with a little bit of electricity, it sticks to the actin and shifts the actin. Right? So the ATP is hydrolyzed right, by the myosin. So remember, there are two binding sites in the myosin. One's called an ATPase, which means it's a what? It's an enzyme that breaks apart ATP. So now you have this ADP, adenosine diphosphate, and this PI stands for phosphate. It's an inorganic phosphate. It's had its energy stolen from it. So now it's just basically like a mineral-like substance. So I had that ATP that had the energy. I plucked that one phosphate off, steal its energy, and just let go of it.
Using ATPase?
Yep, using the ATPase and a little drop of water. Okay, and then they stay attached for a short time. While it's holding the energy, it's going to shift. And then when it's done with that, it's going to let go of the phosphate. It's going to let go of the ADP. Right? Once I do this, so I got this thing charged, I have to have what present at the same time? Something has to move that hinge. Calcium. So on the myosin, we're electrically charging the myosin, but at the same time, we have to move the hinge at the troponin. So the next thing that has to happen is the calcium has to get dumped out of the sarcoplasmic reticulum. This is just endoplasmic reticulum, but because it's in a muscle, we call it sarcoplasmic reticulum. And it's storing the calcium. So when you look at this process, get this thing to turn on, I have to stimulate it with electricity like we did in the lab last week. I zap it with electricity, and it dumps my calcium out. The calcium goes floating across the muscle, and it sticks to what chemical? Calcium floats through the muscle until it binds to what's that hinge called? Troponin. When it binds to the troponin, then it shifts the troponin. And I gave you the example using my tie last week. It shifts the tie out of the way. If there's no excitation and no calcium release, does it matter if I charge this myosin? No, because there's that thing, that tropomyosin in between. It doesn't matter. So you have to have that stimulation and dump out some calcium. And then next you get this thing called power stroke. And you might want to underline that because the next thing we're going to talk about is a power stroke. So a power stroke is the shifting of the hand, that movement. So once calcium's moved the troponin and tropomyosin out of the way, now actin and myosin bind, and now they pull back. That one movement, boom, is a power stroke. Is that one power stroke powerful enough to move your whole arm?
No.
No, it's going to take tons and tons of these things. But that's just one power stroke. Okay, and then the linkage of the actin and the myosin gets rebroken by brand new fresh ATP coming into the picture. So I charged the myosin the first time, and I got that movement out of it. But now it's kind of stuck. What I need to do is bring some fresh ATP in, zap it, and reset it so it can grab again. Without fresh ATP, I can't relax. What do you have to make lots and lots of ATP? Two things. Sugar and oxygen. Yep. So for the mitochondria to make lots of ATP, what would happen if you died? Okay. What if you died and you couldn't provide oxygen to that muscle? It stiffens. Why? Because it can't relax. There's no ATP. You don't have any sugar and you don't have fresh oxygen coming in, so it can't relax. It's stuck in this rigor position, and they call it rigor mortis, right? So you need to have fresh ATP to help relax the muscle. If you don't, then it stiffens up and locks. So after about 24 hours, the muscles will release. They become flaccid again. Is it because suddenly you had ATP? What's happening to the muscles? They're dying, right? So they're digesting themselves. It's a process called autolysis. All the enzymes in there are actually the lysosomes are breaking apart, and the lysosomes do what? They digest things. So they're digesting you. They're digesting that muscle, so the muscle just starts going limp as it starts eating all the protein on the inside. No. It eats your muscles? It eats you from the inside out. I'm not sure. That would be autolysis is what I'm thinking of, but MS doesn't eat you from the inside out either. You work on that and get back to me. Okay. So when you look at the muscle itself, here you have the muscle fiber. Here are the rows of sarcomeres. Remember, this is still the muscle fiber surface out here on the outside, which is called the sarcolemma, which is the plasmalemma for this muscle. So I need to stimulate the outside. I send the signal down through the center through these things called transverse tubules, or what do we call them for short? T-tubules. Yep. So the T-tubules send a signal down to the center of the muscle. The whole time that electricity is shooting down, it's zapping the sarcoplasmic reticulum. What's being stored in the sarcoplasmic reticulum? Calcium. When I zap the sarcoplasmic reticulum, it opens its calcium doors and dumps the calcium out. The calcium starts diffusing all through this muscle, going down into the sarcomere and trying to bind to what? Starts with T, troponin. Yep. This is just a close-up looking at it again. And I have some animated slides to show you. But they're the steps, same steps. So it's the same slide we had earlier. Here's how your book shows the step-by-step procedure. So here you have this charged particle. Right? It has fresh ATP on it. It's going to start binding. It pulls back. When it pulls back, it lets go of the ADP and the PI. What's PI? Just the inorganic phosphate, right. So now it's stuck there. It got rid of that old piece of ATP because it used up the energy. Can it relax yet? What do you have to let it relax? Fresh ATP. So you bring the fresh ATP in and it causes detachment. So here you can see the ATP binds. Causes that detachment, it kicks back into its original cocked position. And now it's ready to bind again. And it will keep going through that as long as you're providing it with ATP, fresh ATP. It'll keep pulling, 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 pulling. What's the one thing that I could remove from the situation that would prevent it from binding anymore, though? Calcium. Yep. So I could take the calcium away and actually stop this process. You have to look at the actin perspective and the myosin perspective. They both have to be doing their part, otherwise what happens? No contraction. So if you have no contraction, what do we call that? Your muscle is relaxed. Okay, so if there's no contraction, you go into this relaxation state. If I take away the calcium, it doesn't matter if I have lots of ATP, can I bind the myosin and the actin? No. So that sliding filaments, they spring back into the original position, waiting for fresh calcium. It's different electrolytes. It can be because of calcium. It can be because of calcium. It can be because you don't have enough oxygen in there to make the ATP. So you're going into that rigor state. There are lots and lots of possibilities. There's another thing. When you talk about electrifying the outside of the membrane, what two ions are responsible for controlling that action potential on the outside of the membrane? Sodium and potassium. So it can be sodium, potassium, calcium. It can be because of oxygen or sugar levels. So it's one of those touchy things that's wide across the board. It can be a lot of them. So the cure-all, they tell you go do what? Drink Gatorade or eat a banana just in case. You get electrolytes from both of those.
So the one part you said, exercise and have to keep doing their job to contract. But at the same time, you have to have fresh ATP
You have to have the fresh ATP for the myosin. You have to have what for the actin? The calcium. So,
and then without either of those, you have to.
nope, not without either of them. Without either of them, you can't get a solid contraction. You need to have the calcium, otherwise you put that tropomyosin in between. They can't touch each other. So I can't move you across the room if I can't touch you. That sounded bad, but you know what I mean. If I can't get a hold of a tug of war rope, the other team's going to win. I just can't do anything with it. So take away my Wheaties and I'm weak. I can't do anything. Take away my hands and I can't grab a hold of the rope. It's a two-part situation. Okay, so what causes detachment? I think maybe I beat this one to death. Oops. So what causes detachment of the actin and the myosin? So how about number one? Calcium binds with troponin. Does that cause detachment?
No.
What's that cause? That causes part of the binding, exactly. So we know number one's wrong. How about number two? ATP binds with actin. Don't be tricked. What's wrong with this question? ATP doesn't bind to actin, right? So number two is wrong. How about number three? ATP binds to myosin. Yes. Remember, the fresh ATP comes in and detaches or unbinds the myosin. So what's wrong with number four? Calcium binds to tropomyosin. Right. Calcium would bind to troponin, but if calcium binds to troponin, what does that cause? Contraction, which is number one. So everything's wrong with that one. Calcium never binds to tropomyosin, and also calcium binding with troponin would cause contraction. All right, so now we take the last steps that we did, and we just add them to this one. So you have this process called excitation, contraction, coupling. When we ended right before the test, when we ended the section that talked about the neuromuscular junction, I talked about the beginning of this. What's the name of the neurotransmitter that has to be released to start everything? Acetylcholine. So this may look like a brand new big step-by-step process, but you've actually seen these before. So acetylcholine is released from the terminal buton. What caused acetylcholine to get released? Calcium going into the terminal, right? So calcium went in, released the ACH. ACH drifts across the motor, from the motor neuron going over to this thing called the motor end plate by diffusion. What's it looking for over here? It's looking for a receptor. It binds to a receptor. That receptor opens up a what kind of channel? Sodium channel. Sodium goes rushing in, causing what to happen to the muscle surface? You're getting a graded potential. You're depolarizing it, right? So you start with a graded potential. When you get enough sodium in, then when you hit threshold, which causes action potential. As soon as you hit an action potential, those voltage-gated sodium channels open up here, and you have an action potential shooting straight down. Just like it went down an axon, it's going down the muscle. So it's going firing. What's this thing it's going down deep into the muscle through? T-tubule. The action potential goes down the T-tubule. As it's going down, it's shocking what? Sarcoplasmic reticulum. So it's shocking the sarcoplasmic reticulum, and it's popping little tiny doors open for calcium to do what? Go into the sarcoplasmic reticulum? Out. Exactly. It's going out of the sarcoplasmic reticulum. Remember, it's crowded. It's compacted. It's crowded inside the sarcoplasmic reticulum. If you open a door, what's it going to want to do? It's going to rush out as fast as it can, right? So it rushes out really quickly. As it's rushing out, it diffuses across the cell from high concentration area to low, trying to find what? Troponin. And troponin is like a little tiny magnet that's attracted to calcium. So calcium gets closer to it, and it pulls it in, and then it binds to troponin. Once it binds to troponin, what's troponin do? It's the hinge that pulls the tropomyosin out of the way, right? So it pulls the tropomyosin out of the way, exposing what? What are these little green things? The binding sites, right? The myosin binding sites where they want to bind to the cross bridge, exactly. So it exposes this myosin binding site. And what did you have to prep the myosin? ATP had to be present. So ATP has this thing electrically charged. It's just waiting. It's looking for that binding site. And now that the binding site's there, what's it want to do? Grab. So as long as you had ATP there, it's going to grab on and it's going to pull back. What's that one movement called? The power stroke. So you get that power stroke. What do I have to do to let that thing go? Fresh ATP, and it brings it back. What if, in the meantime, I turned off the acetylcholine? Think about it. If this is a chain reaction and you turn off the first step, what happens to the whole process? It stops. So if I've charged this with fresh ATP, but unfortunately I turned off this neuron, No more action potentials. What's going to happen to all those little calcium doors? They all slam shut. Is calcium diffusing anymore? Nope. So this is the interesting step. As soon as I close these doors, this sarcoplasmic reticulum goes, holy crap, I lost all my calcium. If you lost your favorite toys, what are you going to do? Gather them back up, right? So you're going to find them. It turns on little tiny pumps. What do you need to run a pump? ATP again. It turns on these little suction pumps that are grabbing calcium really, really quick, and it's pulling it off the troponin. Well, the bad thing is once you've pulled the calcium off the troponin, what's going to happen to the tropomyosin? It recovers those spots. So can this myosin now bind again? Nope. What's it going to cause? Relaxation. Yep. If you can't bind actin and myosin, it causes relaxation. So we just walked through this, and most of these steps we've gone through on other processes. The only thing new here is this calcium actively taken up by the sarcoplasmic reticulum when there's no longer an action potential. I always imagine calcium as these little white marbles, and it spilled all the marbles, and now I'm trying to gather them up again. It reminds me of one of my favorite games when I was a kid. Hungry, Hungry Hippos, right? So the sarcoplasmic reticulum is like Hungry, Hungry Hippos. It's trying to gather the calcium as fast as it possibly can, and while it's gathering the calcium, what's going to happen to the muscle? It's going to start relaxing because it's pulling that calcium off the troponin and causing relaxation. And then we already said this, so it goes back into that relaxation phase. All right, and then number one, relaxation is when the ACH is moved by acetylcholine esterase. What did acetylcholine esterase do to ACH? It breaks it apart. Yep. It splits it, and then what happens to those two pieces? They get reuptake. Yep. So ACH is kind of the best of all three ways to turn off a neurotransmitter. Some will diffuse, it gets broken, and then what's left gets recycled, or what's left gets broken and recycled. All right. And then that calcium ATP ACE pump means that this calcium pump requires what? Energy. Yep. And it's kind of in the name, pump. So as promised, a little tiny animation of what happens here. So this is an old-fashioned animation where it doesn't run on its own. I have to actually click things. But you see the action potential going down the what? Yep. So here's the surface of the membrane. It goes down the T-tubule. It hits this little tiny doorway, basically. It's a spring-loaded doorway. It zaps it, and that spring goes boing. Oh, lost it. Ready? Goes boing. There it is. Better. And then it pops open that doorway. Calcium's crowded in here, so what's it want to do? Rushes out, trying to find what? Troponin. When it finds troponin, it moves the tropomyosin, and then actin and myosin combine, pulling the Z lines closer in. Do the Z lines bend? No, it's just pulling them closer together. And then we already went through these different steps before. All right, so which of the following is true about a muscle contraction? Does an electrical impulse travel down the sarcoplasmic reticulum? No, it travels down the T-tubules. You can cross number one out. How about number two? Calcium is released from the T-tubules. No, it's released from the sarcoplasmic reticulum. So you cross number two out. How about number three? Calcium binds with troponin. Yes, it does. And moves what? Yep, so you might want to circle number three, and then what's wrong with number four then? Where's ACH at? Ask yourself. It's at the junction. Where's actin at? Down deep inside the muscle. So should ACH ever see actin? Never. So number four is wrong. Okay, the next concept we talked about in lab, and it was the twitch. A twitch is how many muscle fibers? One muscle fiber, right? So one muscle cell. And it's just one little tiny action potential that causes what three phases? Action potential happens, and while the electricity is moving and the ions are moving, you have that latent phase. Once, what ion binds to troponin? Calcium. Once calcium binds to troponin, what are we going to get now? The contraction phase, which is phase number two. And then after I turn off ACH, I turn off the action potential, I turn off or close the doors on the sarcoplasmic reticulum, I suck up the calcium. What's the last phase? Causes relaxation. So when you look at the motor units and the twitch, whoops, I squid. Yeah, we were on twitch, right? So the twitch, you need to know those three phases. And hopefully by now you can actually draw one of those. But the latent phase, remember, the action potential is really quick. The ion's moving. the muscle itself is still not moving. This is all the behind the scenes. All those 9 steps we talked about 3 slides back, those 9 steps are all happening during the latent period. So it takes just a few milliseconds, and then you get that contraction. One power stroke after another, after another, after another. Pulling, 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 pulling. And at the very peak, my signal's gone. My calcium's, they call it sequestered if you're looking at the book. Sequestered means it's vacuumed back up. It's pulled back into the sarcoplasmic reticulum. So what's happening to the muscle now? It's letting go and it's starting to relax. And its elastic properties just pull it back into its natural position. All right, next is the motor unit. So we got the twitch out of the way. A motor unit is what? How many neurons? 1 motor neuron. Yep, alpha motor neuron. And what's the other part? All the fibers or all the cells that innervates. So when you look at a motor unit, it looks like this. Here's 1 alpha motor neuron. Where's it coming from? Spinal cord, the dorsal or the ventral side? Ventral, because you know all efferent signals come out of the ventral side. They go down, it's motor, so it's moving you. Here's 1 muscle cell, there's another muscle cell, there's another muscle cell. So it's this 1 neuron going to these 3 muscle cells, muscle fibers. Can it determine which one it wants to contract harder? Nope. When it diverges, it's dumb, remember? It just says off or on. So if I fire this 1 motor unit, I fire all 3 of those fibers exactly the same. They do their little twitch. What if a twitch isn't good enough? Can that motor unit do anything more? So if that 1 twitch isn't good enough, what can it do to itself? Increase the what? Frequency. So that I add twitches, which is called wave summation. Right. So wave summation or twitch summation. And then here's just an example. You can have different motor units of different sizes. Do they have different numbers of neurons? No. They always have 1 alpha motor neuron. What do they change? The number of fibers they innervate. So in lab last week I was telling you, in your eye, so the muscle on the side of your eye, you only have like 5 fibers per motor unit. What's the benefit of having that small motor unit? Precision. You have very delicate movements, very precise movements. In your gastroc, you have 1 neuron, 1 motor unit going to your gastroc, and it innervates potentially 5,000 fibers. What's the benefit of that? Power. It's not there for precision, it's there for power. So motor unit size is important. When you look at what determines the whole muscle overall, so remember, 1 neuron doesn't make the whole muscle contract. It just makes certain fibers in the muscle contract. Here are some of the factors. So the number of fibers contracting at one time is a factor. Of course, 1,000 are going to do a lot more than just 1 fiber. And you can determine that by the number of motor units you recruit at one time. So if I need just a small movement, I just recruit a small motor unit that has a few fibers. If I need a bigger contraction, I can recruit a bigger motor unit. Right? The number of muscle fibers per motor unit makes a difference. Remember, eye versus leg. The number of fibers available to contract. What could happen to these fibers that make them not able to contract? They could have gotten tired or damaged yet. So if they were tired, like fatigued or damaged, that can make a difference. When I hold, if I were to hold my bag, which gets heavier by the day, so if I were holding up my bag and it's like 25 pounds, can I stand here for the rest of the time holding it? Even if I'm holding it fixed, my arm I can already feel is kind of shaking pulling it out to the side like that. But what's happening is that as 1 motor unit gets tired, it starts shutting down. What's going to happen to fix that? Another one's going to go, holy crap, buddy, let me get that. And it'll take over. So the number that are available, what if I hold this for a long time? Are they all going to switch back and forth forever? No. As I get more and more tired, what's going to happen to my arm? Yep, I have less and less fibers that are available to contract, so it gets harder and harder for me to hold that thing. All right, next is the tension developed by each contracting fiber. When we look at the fiber, 1 cell, that 1 cell, how can I get more intense contractions out of it? I turn up the frequency. I increase the number of times the signal goes down that motor unit, and I can make that 1 fiber contract more and more and more. I release more and more calcium, it gets a bigger and bigger contraction. Right? The length of the fiber onset, and we're going to talk about this later, it's called optimal length. We'll talk about that. When a fiber is already completely contracted, are you going to be able to contract it more?
No.
So can you get a supra-maximal contraction? No. 100% is 100%. And then actually the same thing. We'll talk about it. If your arm's completely extended out and the actin and myosin are barely touching, are you going to get a good contraction? No. That's like trying to play tug of war, but only holding on to the last inch of the rope. It's not going to be very effective. Right, and then I already mentioned the extent of the fatigue, but this is for one muscle fiber. If that muscle fiber is tired, then it's not going to contract for you very well. And the last one, the thickness. The difference between you and Arnold Schwarzenegger isn't the number of muscle fibers that he has, it's the size of the muscle fibers. You're born genetically to have a certain number of muscle fibers. You can make them bigger, which we call hypertrophic, or if you don't do anything with it, you know what they do? Atrophy. They shrink down, exactly. Your body's really efficient. If you're not using all of that protein, it will break the proteins in your muscles down and use it somewhere else. A starvation diet, if you're not getting enough food in your body will start eating itself, starts eating its muscles. So working out really hard to try and lose weight and gain muscle, is that a good idea? No, because if you're dieting and you're trying to gain weight, it just doesn't work that way. You break down muscle to provide the nutrients. So the thickness of each fiber. The more actin and myosin, it's like playing tug of war. What's going to be better? Having 10 people on your side or 100 people holding the same rope? It's 100 people. It's kind of a gimme. It's going to be a bigger group of people. It's the same idea. If you have more fibers inside, if you have more actin and myosin inside of a fiber, you're going to get a better, stronger contraction. And that's why people lift weights to get bigger. So they want to get more actin and myosin inside of one muscle fiber. Right. Next point is called asynchronous. What's that mean, A? Without synchrony. So if you're out of sync, you're not working together very well. So asynchronous recruitment of the motor units is what happens. And that gives us a submaximal contraction. Otherwise, if there's nothing really fun to throw, but here we go. So if you had maximal contractions every time you pick up your arm, you would always go, whoa! After I did that, it went up kind of straight and high, and I thought, oh, here it comes. They're going to rush me to the emergency room because I have this little triangular dent in the top of my head from a tissue box. But if you recruited every fiber in your bicep every time you moved it, you'd never be able to imagine drinking water, right? Or hot coffee. That'd be even better. So you get this asynchronous recruitment where you recruit some of the fibers but not all of them, so that you can get the contraction you want. If you want to pick up the bag or if you want to pick up a tissue box or a pencil, you recruit the different numbers of fibers. Right? And then asynchronous recruitment, again, of motor units. Right? For maximal contractions, what you're trying to do is you're trying to fire as many as you possibly can. It's really rare that you fire every fiber in your arm at one time. Have you ever heard of people that they're like kind of scrawny-looking people, but then somebody drives over grandma and they pick up a truck off of grandma? So in that situation, then they were firing everything they had. But guess what? Is that good for them? No. I bet those people, they don't move the next day because their arms are just like, all the fibers are just torn in their arms. So maximal contractions, if you do that maximal contraction, it's impossible to alternate and hold consistently. So they may be able to pick up the car quickly, and if grandma didn't scurry out quickly, what's going to happen to the car? It's coming right back down, yeah. Whether they tear all those muscles and they actually have visibly torn muscles, or they're just fatigued so fast they're letting it down. Maximal contractions are actually really rare. So if I wanted to move this, we'll say a tissue box, maybe it only takes this one motor unit. If I want to pick up my bag, maybe it takes these 2 motor units. If I want to pick up the Buick out in the parking lot, it might take a little bit more than those 3 motor units. But we're going to recruit what we can. And it's amazing how sometimes in the right situations we can do things we didn't know we could do because we never really use all the muscles at one time. There's always a reserve. And then that concept I kind of mentioned earlier, wave summation or twitch summation. With wave summation, do you remember what made it different than... I shouldn't say that out loud. We'll stick with this because not everybody's taking quizzes yet, right? So wave summation, remember, wave summation is talking about one motor unit. What are you doing to the twitches? What's the word tell you? You're adding twitches. You get one twitch after another, after another, after another. How many motor units are we talking about? 1. So you're taking that one muscle and going, that one muscle fiber and just firing it harder. One muscle fiber is barely enough to actually move a whole finger. And I love it when people, and I do it too, when people have that little twitch in their eye. It's like one muscle fiber, one motor unit that's going crazy. And usually that's not enough to get a real good movement. And they're like, oh my gosh, look at my eye. And you're looking at it and there's nothing happening. But it's just enough to make them feel it, but nothing's actually happening in there. Huh? Same problem is when you get cramps. Yeah, electrolyte imbalances, neural signals that are misfiring, all these different possibilities. Brain tumor. Usually it's a brain tumor. I'm kidding. Yeah. I always try to freak people out, and I waited too long on that one and probably didn't do a very good job. Okay, and then when you're talking about wave sublimation, tetanus is when you get maximal contraction without relaxation. So if you're looking at a graph like this, one twitch, you get your action potential. What's this period called? The latent period, where all that 9 steps of ion movement's happening. You get your contraction, where you have power stroke after power stroke after power stroke. And at the top, you turned off the action potential, you turned off the ACH, you closed the doors on the sarcoplasmic reticulum, you started playing Hungry Hungry Hippos with the calcium, and now what's happening? Relaxation. And then you do it again. This isn't very much at all. But just like when we talked about changing the frequency for a neuron, you can do the same thing with a muscle. So fire it once, it starts going into relaxation, fire that sucker again, you get a better contraction. You dumped out more calcium. So you get a better, stronger contraction. With this, you're increasing the frequency so fast, what are you not getting? So what's happening to those little doors on the sarcoplasmic reticulum? They're basically stuck open. So they open up and they're letting all the calcium possible flow out. Now calcium's equilibrated. Are you going to get more calcium out at this point? No. At the top, all of your calcium's been released. You can't release more calcium, so you can't get a more powerful contraction. But tetanus, remember, is maximal contraction without the relaxation. A what? Don't really call it peak. It's just a plateau, probably would be the best word for it. Either plateau or a leveling. Remember, in tetanus, the disorder, like when the bacteria gets in you, what that does is it goes to the, actually releases toxins that go to the motor junction, so the neuromuscular junction, and it causes the acetylcholine to stay out there. It causes those little receptors to stay open, so that you're constantly getting action potentials, and it's stimulating muscle just like this. So it just stays contracted. Where do they usually see the first signs? In the jaw, yeah. So if I ask you a question like this, to get the strongest contraction, which of the following is true? You need 1 power stroke?
No.
That won't cut it. How about number 2? A power stroke's not required.
No.
You have to have a power stroke, right? So it has to be number 3. Numerous power strokes. And I told you we'd talk about this, the optimal length. So optimal length is the best length of the muscle when you get the maximal force. And there's actually, at Iowa State, there's a whole class that focuses on this. I took it. It was a grad level course that I shouldn't have taken, but it was physics and on the optimal length. And the whole course, guess what the main point was? To calculate that the muscle gets the optimal length at 90 degrees when the angle is at 90 degrees. So whenever you bend the joint at the 90-degree angle or midway part of that flexion, that's when you get the optimal length. And the reason it's like that is because the fibers, the actin and the myosin, are at their optimal crossing. If you look at the very peak of this, you've got this ideal location of the actin and myosin binding. What if I pull it way straight, and there's my sarcomere, where this one actin is binding this one myosin? No way, I'm not going to get it. What would happen if I pulled it beyond that, where the actin's actually not even touching the myosin? You get nothing. Yeah, you get no contraction at all. You could probably tore something like Jerry said, but yeah, you've got no contraction, 0 contraction. What if I pushed it so that the actin is actually overlapping the actin, and it's so crowded in there? Is it going to bend? No. Because remember, there's that M line down the middle. It's a plate. You can't push the actin through it, so the actin hits that plate. Can it contract any further? No. So when my muscle's all the way fully contracted, I can't get any more contraction. Right in between is that optimal length. It's the optimal length of the muscle to get the maximal force. I just saved you about $750 worth of one class tuition at Iowa State right there. Okay, so types of muscle contractions, you get isotonic and isometric. And these are the 2 main ones you want to focus on. Iso meant what? You know this. Same. So isotonic means through the contraction you have exactly the same tone of the muscle. Isometric means what is exactly the same? The length. Yep. So we're talking about the length of the muscle. Is it possible to contract a muscle but not change the length of a muscle? If you want to test this, go outside and the sign out in the front in the parking lot, try and pick it up. Are you contracting muscles? Yes. But are you moving the length of your arm? No. So it would be like me trying to pick up this podium with all this mess in it. you go, and you squeeze, you can feel your arms contracting, but there's no change. That's an isometric contraction. Are you burning energy?
Yes.
Yes, you are. Yeah, you're burning energy as far as ATP. If you wanted to go into a physics class and talk about it, technically you're not creating work. So you're not working, but you're burning energy. Isotonic is when you hold the same muscle tension throughout the movement. It would be like picking something up and having the same muscle movement all the way through, the same amount of tension. So in these examples, this one you're actually moving the weight, but the tension stays consistent throughout the movement. But this one you're contracting the muscle. Did the length change? Nope. So what would that be? Isotonic or isometric? Isometric. All right. And I love this. The book sometimes takes a really simple concept and makes it as tough as possible. But it says the velocity of shortening is related to the load. Load is the weight that you're trying to pick it up. What's velocity referring to? The speed, yeah. So the speed that you're moving. So velocity is talking about how fast you can move a weight. It's the fancy way of saying it. And it says, think about this a second. The greater the load, the lower the velocity. In other words, the heavier the weight, the slower you can move it, right? Yeah. And at which a single muscle fiber shortens during an isotonic tectonic contraction, which means that you're moving as hard as you can, but through that movement. The velocity of shortening is maximal when there's no load. In other words, you move your arm the fastest when you're lifting nothing. Brilliant. And then they put a graph, right? So I love graphs. But it's kind of a handy way to make sure that you understand how to read graphs. Here you have the speed of shortening, and here you have the weight, the heaviness, the load. So it says that the heavier the load, so the further you get up on this graph, what's going to do to your speed? Slows it down. So what happened here? You've got zero speed, which means you're not moving. In other words, the weight was so heavy that you can't move your arm. How about up here? There's zero weight in your hand, so you get the fastest movement. Yeah. Yeah, so when they explain stuff like that, sometimes you just think, layperson's terms, come on. All right, so although muscles can accomplish work, much of the energy is converted to heat, and this is kind of an important point too. You're one of the most efficient machines in the universe that we know of. When you look at your car, when you burn a gallon of gas, the efficiency of that's like 1% of the energy that you're burning is actually into moving your car. When you look at your body, about 25% of what you're doing is actually moving you. Unfortunately, the other 75% is burned as heat. When you go walking across the room, test this out. Walk up the steps. You're burning energy going up the steps. How do you know you're producing heat? You're like sweating and you're breathing heavy, which is a sign that maybe you need to get to the gym once in a while more. I'm saying as a hypocrite because I swear they add an extra step every time I go up to the lab. Every time. It just seems like one step longer. I'm going to have to start taking a little break the second tier up there and eat a sandwich or something to get myself the rest of the way. But yeah, so about 25% of the energy that you're burning when you're actually moving is actual energy used for work. The other 75% is just converted to heat. So, like I said, with your car, you've got like 1% that actually going into work, but the other 99% is creating heat. You know, your engine gets at 300 degrees. That's why they have to cool it down so much. And then if you're not moving, so if an isometric, which means what's going on? Iso means same length of all your muscles. Can you actually burn energy without moving muscles? Without moving them, yes. Try, and have you ever done this? They'll tell you lift a weight and hold it there. So you hold it and you hold it. You know you're burning energy because what starts happening? You start sweating, you start breathing heavier, right? And then eventually, when your muscle starts getting tired, you start shaking and you have to let it down. But that isometric contraction, you know you're burning energy, but unfortunately none of it's going into work moving your body, so it's all going as heat. 100% is heat in that situation. So that's an easy way to burn calories. I like to do that on the couch. I like to sit there with my bag of potato chips and my icy cold beverage, and I like to hold things while I'm eating, just to burn the calories as I'm holding. There's physiology at its best right there. Okay, next, muscle fibers have alternate pathways for making ATP. So one of the pathways is called creatine phosphate, and I'm sure some of you actually heard of this. If you go to like, what is it, GNC, yeah. The exercise store, you can buy the stuff in a tub. You buy it, you take it. You store phosphate on creatine in your muscles. So what happens is the creatine is like a little canister. When you need that phosphate and energy, you can pluck that little phosphate off the creatine and put it back on ADP to make it into what? ATP again. So it's kind of like a storage form. And here you can see the equation. Creatine phosphate plus an ADP. You steal the phosphate. There's something called creatine kinase. What's a kinase? It's an enzyme, yeah. So it takes the phosphate, sticks it onto the ATP, so now you have the hollow creatine, and you have an ATP again for energy. It's kind of handy. It's a solute. So think about this. There's a lot of debate on how good this stuff is for you. It's inside your muscles. If you eat this stuff and it goes into your muscles, it will actually store energy, so it helps you work out longer. Does it actually make you stronger? No. It just gives you a little bit more oomph when you're exercising, so you have a little extra energy hanging on there. It's a solute, so as you're building it up inside your muscle, what else is building up in your muscle? Water. You add solute in the muscle, it brings water in, so is the muscle going to change size? Muscle will actually change size, yeah. It gets bigger, but is it stronger? No, it's just holding more water. So I always want to go up to those people you know are taking a little creatine and just take a little pin up to their arm and pop it and watch the water squirt out. Doesn't quite work like that, but it would be funny. Someday I hope to experience the mind, or the world that's in my mind. It's an animated, fun place, I'll tell you. And in the second form, oxidative phosphorylation. What's the name of the organelle that makes this process? You have the mitochondria. It makes ATP, but it has to have two things. Sugar and oxygen. That's why it's oxidative. If you don't have that, what process happens? Glycolysis. So this is the first place. This is quick. This is like Popeye in a can of spinach. It's the creatine is holding on to that phosphate. If you need quick energy, the ADP grabs that phosphate and goes back to work. After that, the mitochondria starts kicking in. And then you start breathing heavy to provide what to the mitochondria? Oxygen. So you get on the treadmill and you're starting to walk. You're like, oh, this is fine, this is fine. Then you start breathing heavy because you've burned up your creatine phosphate. Now the mitochondria wants that extra oxygen to make the ATP. And then at the point where you're breathing so heavy, you're just like, oh man, I got to take a break. Guess what process is working now? Glycolysis. You've burned up your creatine phosphate. You've pushed the oxygen level so low that the mitochondria can't keep up. And now you're using glycolysis. Are you making ATP efficiently? No. Nope. This is your last resort. This is like when you're like struggling to get just a couple more feet when you're running really hard. If you're doing a marathon or something, you're like, oh, I can't make it. What else is building up the whole time that you're... Lactic acid, yep. So you build up the lactic acid. Lactic acid does what to proteins? Acid does what to proteins? What's the name of that process? It's called denaturing. I think I mentioned it like the first week, but you didn't have to remember it. It's called denaturing. If you take a clear part of an egg, which, by the way, we call the white part of the egg, it's clear, that's full of proteins. When you expose it to heat or acid, what color does it turn? It turns white because what happened to those proteins? They started changing their shape and sticking together. The same thing happens to the proteins, actin and myosin, and some of the enzymes in your muscles. When you expose it to too much acid, they start like changing their shape and they don't want to work properly, which causes muscle fatigue. What kind of muscle fatigue is that, by the way? You should know these three muscle fatigues because we talked about them in lecture or lab last week. Causes muscular fatigue. Yep. What was the one at the junction? Neuromuscular. What's the one in the brain? Central. So these are the processes, and your book has this in a little picture. So if you look, here's your ATP. Your first source, when you start burning your ATP, the creatine phosphate, loans the phosphate. If this one wears out, what's the next process? The mitochondria, the oxidative phosphorylation. But what's it possibly going to run out of? Oxygen. So it's making CO2 and water, it's running out of oxygen, and when you start running low on oxygen, glycolysis. And what's the bad product you're making here? Lactic acids overall. Yep. So 3 steps. When you try and replenish that, you'll find that it goes right in reverse. And we'll show you that in a few slides. But first you need to remember those types of fatigue. So muscular fatigue is because of what possible 3 things. Buildup of lactic acid or loss of oxygen or sugar, glucose. Do you have a way of storing oxygen in your muscle? Can it store oxygen? It can. What's the stuff called? Myoglobin, right. So it's like hemoglobin, but it's not. Remember the whole story the first day of class? Geek. But, right. So myoglobin can hold a little. Can you store sugar in a muscle? Yes. Anybody know what the storage form of sugar is called? Glycogen. Yep. So it's called glycogen. Muscles are selfish too. When they get the sugar in, they don't share. It's a one-way trip. Oh, sorry. Clicked way too fast. The next one is neuromuscular. What's it revolve around? What chemical? ACH, acetylcholine. So it's either a lack of acetylcholine or a lack of receptors. And then muscular fatigue. Oh, we already talked about that one. Central fatigue. Brain or spinal cord. So things like ALS would be considered central. There's a damage to the neurons in the spinal cord. Laziness would be an example of central. So psychological fatigue. I want to do it, I just don't want to do it. So increased oxygen consumption is necessary to recover from exercise. They call it oxygen debt. When you're exercising hard, you're burning up the oxygen that's in your blood, you're burning up the oxygen that's inside the myoglobin. When you get low myoglobin stores, the muscle starts demanding more. It's trying to pull more oxygen out. But when the muscle pulls more oxygen, it leaves less for the other organs, so then the heart's going to be deprived, and the brain's going to be deprived, and it's going to start causing you to breathe heavier to bring up levels. You're trying to repay a debt. You pushed it too hard, which is kind of a good thing sometimes. And then what you're trying to do is you're trying to resupply oxygen to the myoglobin and resupply those ATPs. So when you start regaining the oxygen, you turn off glycolysis. When there's enough oxygen, you make enough ATP, you turn off oxidative phosphorylation, and then you start replenishing creatine phosphate. Yep. So it's just the reverse. Creatine phosphate is the first one to supply the energy as a backup, but it's also the last one to get replenished. If creatine phosphate is supposed to be in a muscle, why do we take a test of people's blood to see if they have creatine phosphate in their blood? What's that indicate? Think about it a second. If it's creatine phosphate is supposed to be inside the muscle, why would we test their blood for it? What could have happened? Why? What could have happened to the muscle? Muscle torn, muscle damage, heart attack. Remember, it's your heart too, so think about that creatine phosphate. One of the problems that they have with people taking artificial is that they don't know what the long-term effects on what muscle are. The heart, because it's taking creatine phosphate in, and their heart's doing what? Solute goes in, water chases it. What's happening to the muscle fibers in their heart? They're swelling. Is that a good thing? No, you don't want swelling of your heart muscle. So there's a little bit of a debate because of that. Okay. So creatine phosphate's restored to last, remember, and then the lactic acid's removed and cleared, and then you feel a little bit better, hopefully. That's why they always say get a massage afterwards, because it helps you push the lactic acid out. Or tell you to do what afterwards if you don't go for a massage. Stretch, at least stretch really well. Squeeze your muscles, rub your muscles down, and you flush the lactic acid out. Okay. Next are the fiber types. So there are three main types, and it depends on how deep you want to go into it, but the general three types are these three. Right? If it's not up here, obviously after the test, you probably figured out where do the test questions come from. They come right from the lecture notes. Yep. So there's a reason we call them the notes, because you take notes to study for a test, and so I've given you the notes for the test. All right, fiber types. Slow oxidative is the first one, so type 1. Fast oxidative is the second, and then fast glycolytic is type 2B. So there are two main types that they originally labeled, and then they put a subgroup in between. But the type A's, we call them slow and oxidative because it describes their process. The way that they burn energy is slow. So, in other words, they're really efficient with their energy. You give them a little bit of energy and they can take it a long way. The process they use to make energy is oxidative. What does it need? Oxygen and what organelle? Mitochondria. It also needs a lot of that storage unit for oxygen, which is called myoglobin. Exactly. These slow oxidative fibers, these are the best for endurance type of sports, because those people, they run, and they ran, and they ran, and they ran. What kind of runners would have a lot of slow oxidative fibers in their legs? Marathoners, yep. So marathon runners. We call them red because of that chemical that's holding the oxygen. Myoglobin. What causes your blood to look red? Hemoglobin. It's a similar particle. The only real difference is that hemoglobin's in red blood cells in the blood, causing it to be red when it's oxygenated, where the myoglobin's inside the muscles, it's red when it's oxygenated. So they call it red because it's packed with myoglobin. So does it have a good energy backup system? Yes, which explains why they can keep doing what? Running and running and running. The second type of fiber, I'm going to skip straight to the last one. Fast glycolytic fiber. Exactly the opposite. So are they efficient with their energy? Nope, they burn it up fast. So are these people the endurance type of people? No. They burn up, they're sprinters, exactly. They're like the 50-yard dash. They're not even like the mile runners. They're the ones that go for... They're like the 50-yard dash people. They go, get done running those 50 yards, and they go, oh my God. And they're like all bent over, breathing heavy. And the marathon runners just still cruising right along, right? But these, they burn their energy really quick. When you look at somebody that is like a power lifter, I love it because, believe it or not, I actually come from a family of power lifters. But, so I look at totally... But watching my cousins and my uncles when they're doing their power lifts and everything, they're like, yeah. It takes them 5 minutes of psych up, right? And then they go, ha! And they lift it up, and then they drop it and they go, oh man, woo! Ha! What kind of fibers did they just use? The fast glycolytic ones. It's fast, and they're like shaking it out right afterwards too, because what's building up already? Lactic acid. Yeah, they're like shaking it up. I have the best joke for that. How many powerlifters does it take to screw in a light bulb? 3. 1 to screw in the light bulb, and the other 2 go, yeah man, you can do it, you're buff man, yeah! Obviously I grew up around a lot of Randy the Macho Man Savage WrestleMania stuff when I was a kid too. But yeah, they're extreme opposites. There's a marathon runner, and then these are the sprinters, quick sprinters. The people that are doing, like quick push-ups, and then they're like, oh my gosh. So the type 2B, they use what process to make energy? Glycolysis. So what's obviously not there? Oxygen, which means that storage unit's not there. What was it called? There's no myoglobin. So what color would these fibers be? Red? Nope, they're more clear, more translucent. So they're called the white fibers. The cool thing is they thought, well, you're either born a marathon runner or you're born a sprinter. There's nothing in between. What's kind of neat is that we found that you can actually take these fast glycolytic fibers, and if you start running every day, you can go further and further and further. And what they find is that you take these fast glycolytic fibers and you start converting them into a red fiber. They're not perfect, but what are you adding? They still wear out faster than a slow fiber. You're only adding oxygen. So what 2 pieces of equipment do you have to have in there that you're adding? Mitochondria and myoglobin. Exactly. And it's the myoglobin that makes it look more red. So you've got 2 extremes, and then in between, these are the ones that do like the 5Ks, the 10Ks. They're not quite equipped for the marathon, but at the same time they can go further than the 50-yard dashers. All right. So the 2 big differences, if you look through here, number 1 was the speed of contraction, so how fast they move. Which one wears out faster? The fast glycolytic, and they do a fast sprinting. They're fast, they wear out fast. And the second was the type of enzymatic machinery for ATP production. And the oxidative obviously required what to be present? Mitochondria and what 2 tools? Myoglobin, yep. And this is what helped me remember it. So, have you ever watched a chicken run? Do they run very far? They run like hell. Do they fly very well? They're terrible flyers. They fly for like 5 or 10 feet and then they're done. Then they run again. They run and run. My grandparents had chickens when I was a kid, so I tried catching one. I think they told me to do that to keep me busy, right? So go catch one of the chickens. And they run, and they would outrun me. What kind of fibers do you think they had in their leg? White or red? Red. How do you know that? Because what do we call the leg meat? The dark meat. It's a dark reddish color, right? It's the dark meat. They don't fly very well. What kind of meat is in their chest? White meat. What kind of fibers? The white fibers, right? The fast glycolytic. That's where they go, ha, 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 and they fly for like 5 or 10 feet, and then they're done, right? You ever eaten a duck breast meat? It's delicious, by the way. I had my first duck breast meat at Django, and it was awesome. But they brought it out to me, and I looked at it, and I said, I ordered duck breast. And the guy said, it is. I looked at it and I went, this looks like a steak. Why? It was red. It was extremely red. Are ducks known for their running skills? No, they're known because they migrate, right? They fly for hundreds of miles, and they don't get very tired. So if they're not good runners, what kind of color fibers would you predict in the leg? More red or more white? More white, yeah. They if you try and chase a duck, they go waddle, 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 fly, right? And they're gone. They float on the water and they go waddle, waddle, waddle. That's it. So they don't have a lot of red fibers in their legs. They're more white fibers in the legs. Something to help you think about it. So now you've got a couple examples: the types of runners and then the type of meat in animals. All right, muscle fibers adapt considerably in response, and I kind of already said this. What's the type of fiber that can change? The fast glycolytic fibers can become more oxidative. They add the myoglobin, they add the mitochondria. And so you can actually change your skills. You may not be the best marathon runner if you weren't born genetically predisposed to it, but you can get a marathon in you. All right, so one thing you do is endurance. So aerobic exercise. Aerobics telling you you're requiring what? Oxygen. So you're building more red fibers. Next thing that happens to your muscles, they get bigger. Okay? You don't grow new muscle fibers, you make them bigger in size. Like I said with Arnold Schwarzenegger, same number of fibers. The only difference was, well, I've seen a picture of him lately, he might be bigger. But his fibers were bigger back then. They were hypertrophic. The fibers just added more actin and myosin so that when they contracted, they get more power behind them. It's called hypertrophy. Hyperplasia means more numbers. Is that something that actually happens? No, you don't add new muscle fibers. So skeletal muscle and cardiac muscle, you don't add new fibers to those. If you could add new fibers, what would be the advantage of muscle? If you had a heart attack, what would just happen? You just grow brand new muscle, right? So it wouldn't be a big deal. It's not hyperplastic. It doesn't grow back. Okay, testosterone, and then, of course, the female version would be what? Estrogen. So testosterone is the key player, especially in boys. If a girl took testosterone shots, what would happen to her muscle size? She'd get bigger, yeah. She would just naturally get bigger. She'd have more masculine characteristics, deeper voice, a little bit of hair on her face. Her breast tissue would actually start shrinking. We'll talk about that when we get to endocrine system. But testosterone promotes synthesis and assembly of the myosin and actin. It's building muscle size. Does it make them grow brand new fibers? No, it just makes them grow more actin and myosin, making the fiber itself larger. And then we already talked about this, converting type 2B to type 2A. And then if you don't use it, you lose it. It shrinks. It atrophies. The word trophy or trophic means to nurture. So what's hypertrophic telling you? You're over-nurturing those muscles. If I over-nurture you, what do I make you? Big and fat, right? If I atrophy a muscle that's saying without nutrition, what's happening? It's shrinking. If I don't nurture you, what do? You shrivel up and die, right? Same thing with the muscle. So according to the 40-year-old version, if you don't use it, you do lose it. Different perspective. Right? Limited repair of muscles. So you have these little things called myoblasts. Some books refer to them as satellite cells, but you have some limited repair of muscle. Most of the repair is actually in smooth muscle, but you have a limited repair of skeletal muscle so that if you have them, you have a little bit of damage, they can go through and they patch and they make things better. When you're building muscle, the whole goal is actually to cause mild damage. And I'm not talking about ripping the muscle fiber. I'm talking about ripping the little actins inside. Because if the muscle is contracting and you keep ripping the actin, your muscle says, hey, I've got to build more actin. What's happening to the size of the muscle as you build more actin? It gets bigger. And then if you push that one to its edge and you rip a lot of actin inside of it, then it has to get bigger and bigger and bigger. So it's always good to push it up so you push your limit without actually creating too much damage, too much muscle tear. And then winding through the last segments of this skeletal muscle. So you have inputs that help control skeletal muscle. Can skeletal muscle work on its own without a neural input? Absolutely not. Right, so absolutely not. You can't. I know we did that whole voluntary, involuntary thing, and you say involuntarily you breathe, but can you hold your breath consciously? If you test that with swimming, so You can hold your breath and go underwater. It's a voluntary motion. You can voluntarily hold your breath. What kind of muscles control that? Skeletal muscles. So you have to have a neuron that controls those skeletal muscles, though. If I cut your head off, can you keep breathing? No. Can your heart keep beating? Yes. Is the heart voluntary or involuntary? It's involuntary. If it requires your brain to do it, it's considered voluntary. If you wash your head, guess what? Your GI tract keeps running too. So is it voluntary or involuntary? It's involuntary. All right. So the controls that run skeletal muscle. You have input from afferent neurons. This goes back to that reflex arc. An afferent neuron sends a signal up into your spinal cord, goes to an efferent neuron, and comes back. Do you need your brain completely involved? Nope. Do you need your spinal cord involved? Yes. It's the afferent neuron. It's still part of the central nervous system that's depending on. The second one, primary motor, a better way to say is cortex. Complex is a technical term, but cortex. And I want you to write cortex under here because the primary motor cortex is your ability to do what? Cortex. Conscious movement, right? So you send a signal from, by the way, what lobe is that in? The primary motor cortex. Frontal lobe, yep. So you send a signal from the frontal lobe down and it controls your movements. And then the last one, input from the brain stem. So this you want to think of something like breathing. What's the structure in your brain stem that controls that breathing? Medulla oblongata. You're right, Colonel Sanders. All right. So when we talked about it, and I kind of gave you the overview, but input from the primary motor cortex for fine discrimination skills. So you can play the piano really well. You can move your eyes to specific areas. It's the fine conscious motor movements. And then from the brain stem, think of those involuntary things like breathing. Holding your posture is another involuntary movement. You don't have to think, oh my gosh, I'm slouching, unless there's a cute person looking at you, then you stand up straighter, right? But you just sit there, holding your posture. And then what was the one from the afferent neurons? What was the word I told you might want to jot down? Afferent neurons. Reflex arc. Yep. So you have the receptors that send a signal up through the afferent motor neuron to the efferent down to movement. It's a reflex arc. Super simple.
So when you said that there's a conscious ability from the frontal lobe down to control movements,
that's the primary motor complex or primary motor cortex, right?
is that top down?
You're going way in depth here. It's perception. When you're talking about something like that, that's based on perception.
So that was just an example.
Just an example. Yeah. Okay. And then the muscle receptors. So you have to have a receptor, right? So think about those afferents. We did this in the lab, like the second week of lab, when we did reflexes. We smacked you in the knee, just below. What was that reflex called when we smacked you just below the knee? The patellar reflex, right? So we smack you in the knee, and it pulls on a tendon. That tendon pulls on the muscle. When the muscle is pulled, the muscle freaks out and says, holy crap, I'm going to rip. Those muscle spindles are the receptors, and then they go, whoa, there's too much pull. They send a signal up, and then they come back down, and they tell your muscle contract. You have another one in here called the Golgi tendon organs. These measure tension. Okay? This is determining length. A rapid change in length from pulling your muscle, it goes, holy crap, were you really going to rip your leg off when you tapped it in the knee? No, it was just sensitive to a change in length really quick. The Golgi tendon organs are sensitive to the tension. If I started pulling on your arm, like you're lifting your arm like this, and I start pulling down really hard, and pulling and pulling and pulling, you can control the skeletal muscle and you can hold the tension there, but can you adjust the tension in your tendon? Is it possible you could rip a tendon? Yes. This tendon's super sensitive to that tension. If it gets to the point where the tendon says, this tension's so high that I'm going to rip, guess what it's going to tell your muscle to do? Let go. Just let go of it, and it'll make you drop. That same example is when you try and pick up something that's too heavy. You pick it up real hard, the muscle's still fighting. It's trying to do it and do it and do it. There's going to come a point where you start lightly lifting it down, but there's going to come a point where what suddenly happens? You just drop, right? At the point where you start dropping the tendon, the Golgi tendon organ is saying, you're going to rip if you don't let go. Have you ever tried that? Like you're working out really hard, you really just want to get a little bit more in, and the next day, how's your tendon feel? It hurts, right? It's achy because your Golgi tendon organ is saying, let go of it, let go of it, let go of it. It's trying to control that drop, but you're trying to force it. Do tendons heal very easily?
No.
No. So who has more control? This muscle that's full of blood and circulation, or this tendon?
Muscle.
The tendon will actually overpower it. Otherwise, yeah, you could lock your arm in place, but the tendon will eventually let go. So there's your receptor for the pathway. And the receptor is always at the beginning of what type of neuron? Efferent or afferent? The afferent neurons. Right. That's what we have for skeletal. Next is a smooth. So a smooth muscle acts totally the opposite of skeletal. Even when you look at it, what characteristic do we have with skeletal muscle? It's very striated, striped, right? What about shape? They're long tubes. Are they organized very well? Very well. When you look at them, they're extremely well organized. They're nice and tidy. They're striated. They have multiple nuclei. When you look at smooth muscle, it looks nothing like that. Look at the patterns. I mean, you've got a wide area here, a narrow area there. You've got a patch here that's not even going the same direction as this one, so it's going into the plane. I mean, they're all over the place. They're not very well organized like skeletal is. They do their job, but their organization is just more scattered. Right? We call them spindle shaped because they don't have a tube-like structure. They actually have kind of pointy structure like this. So when you look, it's kind of like this point here, round, and then point. And when you contract it, it just gets more round like a balloon. So they call it spindle shape. No striations. You still have actin and myosin because they do the contractions. But you don't use tropomyosin the same. You have some tropomyosin in there, but you don't use it for blocking anything. And that's on a slide coming down the road, but I'm just pointing it out now. They both have it, but do they both work the same with tropomyosin? No. The other thing is that there's no sarcomere. So do you need a Z-line? Nope. Instead of having sarcomere, you have something called a dense body. So remember, the sarcomere is where the two actins are tied together. Instead, you've got this little dense body thing right here where the actins tie together. And remember, the actins aren't all in one direction like you see before. You've got actins going this way, you've got actins coming out this way, you've got actins going out this way. They're all over the place. They're a scattered pattern. So that when a smooth muscle contracts, it doesn't just contract lengthwise, it contracts roundwise too. It like brings it all in. It's scrunching itself up. I think I covered all of those. Oh, the intermediate filaments, that's the tropomyosin. Intermediate filaments, that's the tropomyosin. And if you don't have tropomyosin working the same way, what else do you not need then? Troponin. You don't need troponin. So there's no troponin. These are not in your notes. I'm foreshadowing. So it's not in your notes. Will it be on a test? No. But this is, I'm telling you, you've got to know this information because when we get to the cardiovascular system, blood vessels are regulated by smooth muscle. Are they voluntary or involuntary? They're involuntary. When we look at the digestive tract, the hollow tubes, do you control and think digest faster? Slow down diarrhea, slow down? No, you don't have control over that. So we'll talk about the different types of muscles in the digestive tract that revolve around smooth. When we talk about the respiratory system has lots of smooth muscle that controls the diameter of the tubes. It controls how you breathe, right? Do you have skeletal muscle in the respiratory system? You have that too, yeah. The voluntary breathing. But the smooth muscle controls the diameter of the tubes, the airway. Control how much air. What are you noticing is a pattern for cardiovascular, digestive, and respiratory? Where do you find smooth muscle typically? Around tube-like structures, right? The GI tract. Cardiovascular is the blood vessels. When you're talking about the respiratory system, you're talking about the tubes that are for airway. Urinary system, the same structures. So when you're talking about the ureters, urethra, smooth muscle. When you talk about the bladder itself, hollow tube, smooth muscle. Right? So you need to know how these things work. The last thing we're going to talk about here will be this: how you use calcium. You use calcium in both situations, skeletal and smooth, but you use it differently. Right? Is there any troponin for calcium to bind to in smooth muscle? Nope. So if you're talking about troponin, you want to think skeletal, not smooth. Right? So this process is slightly different. Calcium's released. Calcium comes into the cell. Calcium binds with something called calmodulin that modulates or modifies the calcium. So calmodulin. The calcium and calmodulin, when they stick together, they activate something called myosin kinase. It's going to be a what? An enzyme. So this myosin kinase is going to be an enzyme that phosphorylates myosin. Phosphorylate is a fancy word for saying it electrically charges it. So basically what it's doing is it's taking an ATP and it's stealing the energy from the ATP and sticks it on the myosin. And then now that you have this phosphorylated myosin, what's it want to stick to? What's myosin want to stick to when it's charged? Actin. So that's a gimme. When you charge the myosin, it wants to stick to the actin. So now it's going to bind, it's going to start pulling, and it's like crossbridge holding on and pulling. So here's just a little picture diagram. You've got the calcium that comes into the cell. Calmodulin is what it binds to, not troponin. Now that modified calmodulin activates that myosin kinase. It steals the energy from a phosphate, ATP, and charges the myosin so it can bind to actin. Yep, it steals an energy from an ATP, so it's from that phosphate. And the last thing you have to have down is the primary source of the calcium is not the sarcoplasmic reticulum. The primary source is the ECF. What does that stand for? Extracellular fluid. So the primary place that calcium goes into a smooth muscle isn't from sarcoplasmic reticulum, it's from the blood and the interstitial fluid around it. So the calcium comes in, it binds to that calmodulin. Calmodulin activates the myosin kinase. The myosin kinase phosphorylates the myosin, which charges it, and then myosin binds to actin. There's no need for T-tubules. You don't have to worry about those. And again, there's no tropomyosin. Troponin. The tropomyosin, remember, helps shape the cell. It doesn't help contract. So your book compares a side-by-side comparison. What's happening in smooth versus skeletal muscle. So smooth muscle, you excite it. The calcium comes from where?
ECF.
ECF, outside the cell. It goes in, binds to calmodulin, so it's a series of biochemical reactions. Calmodulin, myosin kinase, activates the myosin, and then it moves the cross bridges. We talked about skeletal muscle. Skeletal muscle, where's the calcium come from? Sarcoplasmic reticulum. So from the sarcoplasmic reticulum, it goes down, you know, the whole stimulate the sarcoplasmic reticulum, dump out the calcium, bind troponin, move the tropomyosin, actin myosin bind, fresh ATP comes in, relaxes them, and then you got the process. So know how to compare these two. Two different processes. It's 2:29, so we'll end with the question. When you want to get rid of the calcium in a skeletal muscle, what do you do to it? You hungry hippo it and pump it back into the sarcoplasmic reticulum. The same thing works here. When you want to get rid of calcium, you hungry hippo it with pumps, but you move it where? Back outside. If those pumps are only on the walls of the cell, is it going to be a fast process? No. It's a slower process. And it's exactly 2:30, so that's where we're stopping. Remember, if you didn't do the homework, make sure you get it done for Tuesday. Nope. Since there's nothing... Oh, actually I should have, since there's homework due. Crap, I should have had a sign sheet. I'll just trust you. I don't have the paper on me. You want to sign something? I trust you here. Your name's Megan, right? Magic.
You say that pt2 makes like water in your muscle or is it water?
It goes in your muscle and holds phosphate, and then it attracts the water with it. No, it has nothing to do with that. It just holds the phosphate so that you have a quick energy, like a backup. See that?